Hello everyone, my name is Jacob Halusek and this is my submission for the Applied Statistics final. Here's my Bearcat ID card. Let it focus in there real fast. There we go. My M number is M08736098. And now that we got the identity verification out of the way, let's begin with the test. So, question 1 states that in this study that we are given, we have two independent random samples with interval ratio data, where the interval ratio data was collected. In group 1, we had a random sample of 133 primary hypertension patients that were taken, and each person's total cholesterol was measured in milligrams per deciliter. It was recorded as well. In group 2, a random sample of 41 normotensive patients was taken and their total cholesterol was recorded. Data is displayed in the table. We are told here to use a 5-step hypothesis testing process to see if our pH group's population total cholesterol level is significantly higher than 210 milligrams per deciliter, using alpha equals to 5%. So what that tells us is that it helps us set up our hypothesis down here. We have to use the 5-step hypothesis testing process. We know we're focusing on this pH group right here, and we know that we're testing to see if the cholesterol level is significantly higher than 210 milligrams per deciliter. So our null hypothesis is going to be that our mean is equal to 210 milligrams per deciliter, and our claimed alternate hypothesis is that our mean is greater than 210 milligrams per deciliter. Next step is going to be finding our critical values using the right tail test, because we are looking to see if our mean is greater. So we know we are looking to the right side of the normal distribution table. So to figure that out, we take 1 minus our alpha, which is 0.05, to get our z-value, which is 0.95. Now when we go use that and apply that to the table that we've been given, but we also know this from taking notes, using it so much throughout the homeworks, that a z-value of 0.95 is equal to a critical value of plus 1.65, plus because we are on the right side of the normal distribution curve, remember. Step 3, we are going to compute the test value. We know that x bar is our sample mean, our mu is our hypothesis population mean, that's our we have our sample standard deviation, and n is equal to our sample size. We take all of our variables, we plug that into our z-value formula right here. We replace all of the variables with the numbers we are given, our sample mean being 214.71, our mean here being 210, this guy, our standard deviation being 29.66. That's simply found by taking our population variance and finding the square root of that to get rid of the squared symbol there. Then we're dividing that by the square root of 133, being our sample size. Sorry, had to adjust that there for a second. It was looking weird. Moving on. So once we go ahead and figure all of that out, we run through, plug in the calculation, we get a 1.83. So now step 4, making our decision based off of our data and our information we have here. Our test value of 1.83 does fall within our critical range because it is past our critical value of 1.65. It's on the right side of that normal distribution curve. So it's greater than 1.65. Therefore, we will reject the null hypothesis. Now, summarizing the results into a better formatted sentence, the null hypothesis will be rejected. There is enough evidence to support the claim that the average total cholesterol level is significantly higher than 210 milligrams per deciliter. Moving on to question number 2. In this study, it's the same setup as before. We're given our table of all of our primary hypertension patients. We have 133 of them taken, a sample of 133 taken, our sample mean being 214.71, and our population standard deviation 29.66. We figured that out before. They go ahead and set up the table for the normotensive patients as well, putting in all their data. Part 1 of question 2 is asking what is the point estimate of the primary hypertension patient's total cholesterol, and what does it mean? So a point estimate is a specific numerical value estimate of a parameter. The best point estimate of our population mean is our sample mean, x bar. So the best point estimate of the primary hypertension patient's total cholesterol level is 214.71. We get that just by looking right here, our sample mean 214.7 or 214.71, yeah. Oh Lord. Part 2 of question 2. We are to find the standard error of the sample mean of the primary hypertension patient's total cholesterol. So the formula for standard error of a sample mean is equal to the standard deviation divided by the square root of the sample size, right here. So then we go ahead and we take our numbers that we have up on our table here, plug them in to our equation where they belong, go ahead and solve that, and we get 2.57 for our standard error. Now, can we apply the central limit theorem to the estimate the population mean of the primary hypertension patient's total cholesterol, and why? Yes, we can. Since our population standard deviation is 29.66, we would at least need a sample size of 30 or more patients in order to use a normal distribution to approximate the distribution of the sample. Sample mean, sorry. The larger the number we have, the more accurate of an estimate we can make on the whole situation. We have a sample size of 133 patients, so we are well over the needed number of patients in order to use the normal use the central limit theorem. Part 4 of question 2. Find a 90% confidence interval of the population mean of the primary hypertension patient's total cholesterol. Also interpret what its meaning would be. So it's telling us to use a 90% confidence level, giving us a z-value of 1.65. We've covered that. We know that just from class examples, looking through the table, we use it a lot. Confidence interval formula that we're going to use is going to be taking our sample mean minus subtracting our z-value. This is for the lower end of we're basically setting up a containment boundary sort of thing, saying like it can't go further to the left, can't go further to the right, our mean needs to be right in the middle. So we are taking our sample mean and we are subtracting our z-value times the standard deviation divided by the square root of our sample size. And we're saying that that is going to be less than our mean, and that our sample mean plus our z-value times the standard deviation divided by the square root of our sample size is going to be greater than our population mean. So once we go ahead and plug in all of our values into the corresponding variables based off of all the information we have before, 214.71 is our sample mean listed right here. 1.65 in for our z-value, which we know right there. Our standard deviation is given up here of 29.66. And our sample size n is given right here as well, 133. So we go ahead and plug in all of our numbers into our variables, go through, punch them out, solve it, and we are left with the values 210.47 is less than our population mean, and that 218.95 will be greater than our population mean. So making sense of it all, interpreting the meaning of those of the critical range that we got there, we are saying that we can be 90% confident that the true mean of the total cholesterol is between 210.47 and 218.95. Moving on to question number 3. So we're given some information here, told to apply the chi-square test of independence to our example. We have a random sample of 100 or 500 U.S. adults who are questioned regarding their political affiliation and opinion on tax reform bills. We are testing if the political affiliation and their opinion on a tax reform bill are dependent at a 5% level of significance. The data is put into this contingency table here. So part 1 of 3, we are to describe the relationship between the political affiliation and opinion on tax reform. So the best way to really know the correlation to see if there is one at this 5% is what we're given is we need to run through a hypothesis test. So we are going to not hypothesis test. We're going to run a chi-square test in order to see the correlation between the two. So start off by giving our hypothesis that the null hypothesis is that the political affiliation and their opinion on a tax reform bill are independent at 5% level significance. This is not the claim we're looking for. The claim we are making is that our alternative hypothesis, the political affiliation and their opinion on a tax reform bill are dependent at a 5% level of significance. Step 2, we are going to be finding the critical values. So first off, we need to go through and find our degrees of freedom. Degrees of freedom is equal to the number of categories minus 1 for chi-square testing. So we're going to take 3 minus 1 gives us 2. Moving on, we are going to take our critical, find our if I could talk, that'd be nice. Our critical value equals 5.991. We know that the degrees of freedom is equal to 2, and we are given the alpha being 5%. We are able to locate the critical value on table G. So go over to table G, that was given to us the chi-square distribution. We go to our degrees of freedom, 2, down over to our alpha being 5% or 0.05, and we are giving 5.991. Moving on to step 3, we are to compute the test value. Now the formula given to us is chi-square equals the summation of the observed values minus the expected values squared divided by the expected values. And that's running through this matrix finding, adding all of these together. I found a way through the book and online where you can use your TI-84 graphing calculator to solve this. You add all the data into a matrix and run a chi-square test for independence in it. So here you can see I have my 2x3 matrix set up. I plugged in all the data right here. Took the data from these 6 cells, plugged it in, found the chi-square test for independence within the testing area on the graphing calculator. Punched in that my observed is A and my expected is B, calculated it, and I got my chi-square test of chi-square equals to 22.15. Now I'm making a decision based off the information we figured out just here. We are going to reject the null hypothesis because there is enough evidence to conclude a dependent relationship. Our chi-square value we have here is greater than the critical value, and therefore we have enough information to conclude a dependent relationship between the political affiliation and the tax reform bill opinions. Putting this into a summary, the null hypothesis was rejected. There is enough evidence to support the claim that the political affiliation and their opinion on a tax reform bill are dependent at a 5% level of significance. Part 2 of question 3 had us calculate a chi-squared statistic and check the independency of the two variables, political affiliation and opinion on tax reform, using alpha at 1% now. So we're really just going to be running through the same whole thing we just did, only switching out our 5%, the 5% it told us up in here, for level of significance, for 1%. So our null hypothesis, our degrees of freedom, sorry, not our degrees of freedom, our critical value is going to change, all because we are changing our level of significance. So going through, the new null hypothesis will be the political affiliation and their opinion on a tax reform bill are independent at a 1% level of significance. That is still not our claim. Our alternative hypothesis is that the political affiliation and their opinion on a tax reform bill are dependent at a 2% level of significance, and that is what we are claiming. We then move on to step number 2, finding our critical values again. Take our degrees of freedom, which is the number of categories, minus 1, which is 3 minus 1 gets us 2. Then we know that the critical value will be 9.210. Again, we know that because we have our degrees of freedom here, 2, and our alpha at 1%. And we come down to our chi-square distribution table, down to our degrees of freedom 2, scroll on over till we get to alpha 1%, 9.210. Step 3, computing the test values. Again, the chi-square equation to figure out, go through the contingency table and get the chi-square value. I went through the calculator, set up that same matrix, ran it through all again. It doesn't change because we didn't change anything within the matrix itself, or we didn't change our degrees of freedom. The only thing that ever changed was our critical value because our level of significance changed. So we get the same result of 22.15. We are going on to step 4 to make our decision based off the data we have collected or calculated. We will reject the null hypothesis again. There is enough evidence to conclude a dependent relationship. So putting this into a summary, the null hypothesis was rejected. There is enough evidence to support the claim that the political affiliation and their opinion on a tax reform bill are dependent at a 5% level of significance. That is supposed to be a 1% level of significance. Sorry about that. Moving on. I was just checking to make sure I didn't miss that anywhere else. Alright, moving on. Question number 4. A small study is conducted involving 15 infants to investigate the association between the gestational ages at birth, our X value, and that's going to be measured in weeks, and our birth weight, our Y value, measured in grams. So you can see all the data here listed into our table. Infant ID number listed 1 to 15. Gestational age in weeks, we have it all listed here. Our birth weight in grams, all listed here. So first things first, we're told to calculate the Pearson's sample correlation coefficient, or find R value, and interpret what that meaning is. So my R value came out to be 0.8793. Basically, the range of correlation coefficient is from -1 to +1, and -1 being very weak and in a negative pattern, so going down, and our +1 being strong and going up. We have 0.8793, that being pretty, I'd say moderately strong. It's a positive correlation as well. If we look down on our graph here, it's a little scattered out. It's not perfectly in a straight line, but it's not all spread out everywhere. It's condensed, and you get the idea of where the trend line will be going. So I found the R value, this correlation coefficient, by going into Excel. I plugged in all my data. Here I got my gestational ages in weeks. I got my birth weight in grams right here. I then found the correlation coefficient by creating this function right here, which is equals CORREL, or Correl, for correlation. And then we are going to take this data array right here from column B, from B2 all the way down to B16. and then we are going to take that being our x values, and then our y values we're going to take from this data array right here, being from C2 all the way down to C16. Then we click enter, and it pops out this R value for us right here, 0.8793. Moving on to part 2 of question 4. We were told to test the hypothesis that the probability would be equal to 0, so that we would have a straight line correlation between the gestational ages and the birth week, or the birth weight, sorry. So step 1 is to hypothesize and state the claims. Our hypothesis going to be the probability equals 0, and that being our null hypothesis, and then our alternate hypothesis being that the probability is greater than 0. Step 2, moving on to find the critical values. We are told to go with alpha equals 5% again, so 0.05. Going into our degrees of freedom for t distributions, degrees of freedom is equal to n minus 2 now. So we have 15 being our sample size, subtracting 2, getting us 13. Going into the t distribution table, we take our degrees of freedom, scroll down to here, go across, till we find our one tail, again, because we are trying to see that our probability is going to be greater than 0, going to be a one-tailed hypothesis, going to be right-sided. So one tail at alpha being 5% or 0.05, matching up to our degrees of freedom at 13 equals 1.771. This is going to be positive because we are on the right side of that normal distribution curve. Moving on to step 3, we are going to compute our test values. So we know R is equal to the correlation coefficient, and N equals our sample size. So go ahead and we'll go through, and we have our equation here that the T is equal to the correlation coefficient times the square root of N minus 2 divided by 1 minus R squared. Take all of our values that we have, plug them in for the variables, go through, solve it, simplify, and we are left with 6.6567. Step 4 is to make a decision. Our test value of 6.6567 is greater than our critical value of 1.771, and therefore falls within our critical range, so we will reject the null hypothesis. Step 5, summarizing. The null hypothesis will be rejected. There is enough evidence to support the claim that the probability will be greater than 0. Then lastly, part 3 of number 4 is we are to fit the line of best fit of y on x. Use this model to estimate y when x is equal to 18 weeks. Now, like I said, I went through and I plugged everything into Excel. I created a scatter plot, got my trend line in there. I have my R squared value up here, right here, and I also have my the equation for this line right here. So my trend line equation came out to be y equals 182.15 times x minus 4010.6. So I go ahead and take our x equals 18, plug it into where x is, simplify that, and I am left with y equals negative 731.9. And that is the end of the test. Thank you very much for listening. I've had a very enjoyable semester learning with you. I've learned a lot, and thank you for everything. Appreciate it.